Hi there. We're going to go over the first chapter of the Introductory Chemistry book by Kevin Revel. So we're going to be looking at this one note here with the slides in it. And so let's see if we can get that. These slides do have the Kevin Revel's notes in them, so we'll touch on those a little bit, but there's a lot of stuff here for you to read. So as I said in class the other day, that chemistry at just about anything you think of at one level or another, you can think of it as involving chemistry, and you see lots of examples here. And obviously, if you're planning to go on to a career in science or medicine or technology or engineering, anything like that, chemistry is one of the basic things that you need to have some understanding of. It's also, chemistry is a place where you learn to do advanced problem-solving kind of skills that are quite sophisticated, and we focus a lot on making sure that we understand how good our answers are, and can kind of self-critique our answers. So there's a lot of good practices, I think, that come from chemistry, as well as its fundamental involvement in a lot of things. So chemistry is the study of matter and its changes. And matter is defined as anything that has mass and takes up volume, and that matter changes from one form to another through chemical reactions. We also say the study of matter and its properties. For example, gold isn't very reactive. Lead has a high density, so does gold for that matter. Gasoline reacts with oxygen and produces carbon dioxide and water and some other stuff maybe, and gives off a lot of energy. These are all properties of different types of matter. Chemistry, we talk about, when we talk about matter, we talk about the composition and the structure. Composition is just simply what's present in the structure. So it might be the percent, maybe of carbon, the percent of hydrogen, the percent of oxygen that are in something, or it might be a formula. We might talk about, for example, C6H12O6 is one thing that formula stands for is glucose, which is what we call blood sugar. Structure talks about how it's made and how it's arranged. So there's actually a lot of different things that are C6H12O6, depending on how the C's and H's and O's are arranged. You get different compounds. Glucose has that structure. Fructose also has that formula as well. So the actual arrangement in space of it, how things are bonding between the atoms. We talk about shape eventually of molecules as being a big part of that. So when we talk about types of matter, the first thing we typically talk about are these two pure substances, elements and compounds. Elements are on the periodic table. That's one way you know it's an element, if it's on the periodic table. Compounds can be broken into elements, okay, but elements can't be broken down into anything else. If I try to break that down, it doesn't go, but this way these can be broken down into elements. The fundamental units of elements and compounds. Compounds are typically made up of molecules, although sometimes we'll talk about something called formula units, which are sort of different from molecules, but it's a small distinction. And then elements are made up of atoms, although sometimes you have some molecular elements we'll talk about in a little bit too, where it's the same atom but there's more than one of them. So here is water, and this, if it had a couple of dots here to represent the electrons on it, that would be called a Lewis dot structure. It has a suggestion of a little bit more information there. That angle is 104 degrees, I think, in water, and that structure certainly sort of suggests that angle appropriately. This is called a space-filling model. Where the big red thing is the oxygen, and the two gray things are hydrogens. So we have different ways of representing things. And one of the challenges in chemistry is to be able to think about all those different levels of representation. You know, water might be a solid at a low temperature. It might be a clear, colorless liquid at most temperatures, or it could be a gas at high temperatures. But they're all H2O, and however it exists on the bulk level to us, at the molecular level, it looks like these molecules here, and again, probably the space-filling model is the most accurate representation, but the Lewis dot structure with a little bit of shape in it might be a easier to understand representation. But understanding all those ways of thinking about it, from the big to the very little, is one of the challenges of chemistry. Here, it said before something about the elements that occur naturally as molecules. There are 7 elements that occur as diatomic molecules. I've written a little diagram of the periodic table, part of the periodic table over here. I've added hydrogen right above fluorine. There's reasons to put hydrogen there, although it's usually not written there. But nitrogen, oxygen, fluorine, hydrogen, chlorine, bromine, and iodine are the 7 diatomics. They exist in nature as molecules that have 2 atoms of the element in it. So again, some elements will exist that way. So the air that we breathe contains mostly N2 and O2. The O2 is what we have to do respiration. The little number at the bottom is called a subscript. Here we have a picture of water flowing from a copper faucet, and you see the idea of the bulk. You know what the copper faucet looks like, what the water looks like, and you can probably imagine how those would feel and what they would do, what kind of properties they would have. And then the molecular representations as little pullouts here in these pictures. And again, one of the challenges is to be able to see both of those when you look at something. Mixtures are a impure type of matter. Okay, so this is impure. It's got different substances, but they're not necessarily bound in a fixed ratio. So, for example, H2O is always 2 H's and 1 O. That's a fixed ratio. Hydrogen peroxide, H2O2, is always 2 H's and 2 O's. And if you buy hydrogen peroxide in the drugstore, it's a 3% mixture of hydrogen peroxide in water. So it's a mixture of hydrogen peroxide. Hydrogen peroxide, you can have concentrations of this from basically 0 up to about 30% as the ones that I've seen. And so typically what they sell in drugstores is supposed to be 3%, but the hydrogen peroxide in water, it's not a fixed value. It can be a particular value for a particular sample. But if you set out to make a solution of hydrogen peroxide in water, nothing says it has to be 3%. So bronze here is a metal that is a mixture of copper and tin, and again, it's not a fixed ratio. If you change the ratio to copper to tin, you might get different properties in that metallic alloy. Now, when we talk about mixtures, we divide them into two categories: those that have a uniform composition, and those that don't have a uniform composition, or we say those that mix evenly, are called homogeneous mixtures or homogeneous mixtures, and components that don't mix evenly are called heterogeneous mixtures. So you see the salt and water on the left, and then the sand in water on the right, and the sand settles out of the water for the most part, even though maybe you'll see a little bit of sand floating around in the water, like when a creek gets muddy or whatever. But they're not uniform mixtures. So if you can imagine taking a sample from different parts of that container, you might get different mixtures. Here's some other mixtures here. Chocolate chip cookie dough is a heterogeneous mixture. Coffee is a mixture. Coffee is more homogeneous probably, unless you let it sit for a long time. Air is probably a more homogeneous mixture as well. You see that on the bottom right. And in the top, you're seeing a reaction being carried out in a lab where someone's pouring one substance into a beaker with another substance, and something's happening. You see that white cloud, which represents a precipitate, that's being formed, and at the molecular level, you see the crystals of the precipitate. So the green and purple things that are forming here, that is the white solid. Precipitate, or PPT, more commonly written as PPT for precipitate, that is forming there. To separate mixtures, we can do this, separate using what we call physical processes. So you see here a filtration. You might, other physical properties might be distillation, where you heat up a sample until one component boils off as a more pure vapor, and the other component, because it has a higher boiling point, stays behind. So distillation is a way to separate mixtures that are liquid and have boiling points we can easily reach. And there's lots of tricks to play with that. You might see something called sublimation, which is the same thing, except you're going from a solid directly to a gas in sublimation. Distillation, you're going from a liquid to a gas and then condensing that gas back to a liquid. You might see other physical processes might be crystallization, where somehow we arrange things so that something that's in solution comes out of solution as a pure crystal, and the crystals tend to, because the molecules or the formula units like to stack with similar molecules and formula units, crystals tend to be more pure. So that's another technique. But anyway, these are physical processes, and the big thing about a physical process is that you're not seeing any kind of chemical change. Right. So if I take water that's a liquid and I convert it to water as a gas, those are both still H2O. So there's no chemical change. If I take water and I pass an electrical current through it, which I'm going to represent with a E with a naught on it there, I can get hydrogen gas and oxygen gas. That is a physical, chemical change, because we're going from liquid water, from H2O to H2 and O2. So that's the difference between a physical change and a chemical change. Okay. So here's a little flowchart diagram of matter, dividing it into pure substances so you see that matter is divided into pure substances and mixtures, and then pure substances are divided here into elements and compounds, and mixtures are divided into homogeneous mixtures and heterogeneous mixtures. Oftentimes homogeneous mixtures are also known as solutions. Well, it's trying not to write on me. So homogeneous mixtures are known as solutions. Solutions there. Let me clean that up just a little bit. All right. And then when we start talking about matter and physical changes in matter, we tend to rely on an idea of three states of matter, that you have solids that have definite shape and volume, liquids which have a definite volume but take the shape of their container by gravity, and then gases which have no definite shape or volume. So that's the three phases of matter. There's some other ones. There's another phase that we talk about sometimes called a plasma, but we don't need to worry about that in this course or in most introductory chemistry. So if you look at the molecular description of this, you see that in a molecular model, the solids are very rigidly arranged. They're not moving very much. And then if you heat them up, which the process is called melting, you can get a liquid, and the liquid molecules are still sort of interacting with each other, but there's a lot more motion there. That's not such a rigid structure. And then if you heat the liquid up, that's called vaporization, and you get gases, and in gases the molecules are widely scattered. They're far apart. They're moving quite rapidly. The higher the temperature, the more rapidly they move, and they're hardly interacting with each other at all. And then if you cool the gas down, you get condensation. And I'm sure you've all seen, days when water has condensed onto the windows or something, like it's doing today, where there's a lot of humidity in the atmosphere, and if the inside of the window is cool, like if you're running an air conditioner or a fan, the water may condense out of the atmosphere onto those windows. And then if you cool it down further, the molecules freeze into that solid form. So that's a description of those changes. Now, kind of the premise of chemistry is that, at least of the atomic model of chemistry, is that if we look at the arrangement of the particles that compose the substances, so the different atoms, that the way those are arranged is going to influence the properties of that matter. So you have here liquid gold being poured into a mold to form a gold brick, and how when they're in the liquid form they're kind of jumbled around, and then when the solid brick has this rigid array that you can see that almost looks kind of like a honeycomb pattern there of those atoms. So I talked before about physical changes and chemical changes. Now we're going to talk about physical properties. And so there are listed here some physical properties: mass, volume, temperature, color, and hardness. These are all things that can be changed or can be measured without changing the identity of the substance. That is to say, without a chemical reaction. So if I melt copper to determine its melting point, it's still copper. After it melts, it's liquid copper. So, melting point, might be, or the freezing point. These might be properties of a substance that are physical properties. So water, for example, freezes at 0 degrees Celsius, and it melts at 0 degrees Celsius. I'm sorry, those are the same point, aren't they? So what I'm also talking about is the boiling point. which is, of course, the same thing as the condensation point. And for water, those are at 100 degrees Celsius, and that's no accident. That's the way they set up the Celsius scale, was they put the freezing point of water at 0 Celsius and the boiling point at 100 Celsius, and then divided the thermometer up into 100 divisions between the two to get the size of a Celsius degree. You may know these in the Fahrenheit versions as 32 degrees Fahrenheit and 212 degrees Fahrenheit. We won't use Fahrenheit very much or at all in a chemistry class, except to do conversions to Celsius. One thing you might notice is just that's 180 degrees Fahrenheit. This is 100 degrees Celsius between the boiling and freezing points. Which degree is bigger, a Celsius or a Fahrenheit? Well, it takes more Fahrenheit degrees to accomplish the same temperature change, So actually degree C, 1 degree C is equal to 1.8 degrees Fahrenheit, but there's also a difference in the 0 point. So you'll see when you see the equation, your degrees Celsius temperature, which I'll write as T/degree Celsius, is going to be 1.8 times the temperature in degrees Fahrenheit plus 32 to correct for sorry, that's minus 32. Sorry, minus 32, and the parentheses here for that. Yeah, I totally botched that equation. Let me fix that. Try that again. Temperatures in degrees Fahrenheit are going to be 1.8 times the temperature in degrees Celsius plus 32 to correct for that difference in the 0 point. You'll see that equation later on, but I just wanted to preview that for you. So again, these properties don't change the identity, and phase changes going from solid to liquid to gas and back and forth are physical changes, not chemical changes. Chemical properties cannot be measured without changing the identity of a substance, and chemical changes change the identity of the substance. So you see here a little fire, and that is a combustion reaction, and the chemical property is called flammability. And what's probably happening here is we have some wood that is some amount of carbon, hydrogen, and oxygen. So I'll call it C sub X, H sub Y, O sub Z, where I don't know X, Y, and Z are. And it's reacting with oxygen, and it's giving us mostly CO2 and water, although that's a kind of a purist view of it. There might be other stuff left behind, if you know from experience of a fire, you kind of ash and stuff, so we might have to explain that, invoking things like partial combustion and stuff, but that's a chemical reaction. I will point out that not chemically reacting is also a property. It's also a chemical property, even though you don't change something to measure that property, you try to change it, right? So the fact that gold isn't very chemically reactive is a chemical property of gold. And so here is an image of a pretty dramatic reaction where zinc is reacting with sulfur, and you see that a lot of energy is being given off in that reaction, and it forms a compound that we call zinc sulfide, which is a new, different compound. And so you see the atomic model of the reaction there, and of course this arrow is read as yields, and the things on this side are what we call the reactants, and the thing on this side is things over here are called the products. So here is a chemical reaction you may have seen. You've got natural gas burning on a stovetop, and the natural gas is composed of a compound called methane, which is this CH4 compound here, and one molecule of that reacts with 2 molecules of oxygen to give us 1 molecule of carbon dioxide and 2 molecules of water. And notice that the number and type of atoms on both sides of this reaction are the same. This is what we call a balanced equation. And when you see number and type of things are the same on both sides, that sort of statement, sometimes the word we use for that in science is we say that those are conserved. And I misspelled conserved. Spelling is hard, chemistry is easy. C-O-N-S-E-R-V-E-D, conserved. So if we were to write this in chemical language, we would say CH4 plus, okay, I've got two O2s yields CO2 plus two H2Os. And if I count that out, I've got on this side, I've got 1C, 4 H's, and 4 O's. Over here, I've got 1C, I've got 4 H's, and I've got 4 O's. So those are the same. So again, chemical changes change the identity of the substance, or you have to try to do that. Physical changes do not change the identity of the substance. Now, energy is often associated with chemical changes, and you'll see that that's an evidence of a chemical change. We talk about potential energy that's stored, and kinetic energy, that's energy associated with motion, and energy itself is defined as the ability to do work. If you think about a battery contains a chemical reaction, and if that battery is put into a device so that the circuit's complete, then when the device is turned on, the chemical reaction occurs. Potential energy that's stored in the form of the reactants that are in there, the battery, is expended and converted to kinetic energy, which then runs the device, your cell phone or whatever it is, and does work to do that. And as that's happening, that potential energy goes down, and eventually the battery reaches a point where it has insufficient potential energy, and you have to recharge the battery, to give an example of that in chemistry terms. So in this case, heat energy is going to increase the kinetic energy of the particles, and if you apply heat, that's going to make the particles move faster, and that might change what they're doing. It might make them more reactive. Here you see examples of biking where you're having a energetically spontaneous process where you're coasting downhill, as opposed to an energetic process that you have to put energy in, where you're moving up the hill. The one where the energy is being given off freely is called exergonic, and ones that are where you're putting in is called endergonic. Erg relates to energy. X means coming out, end means putting in. So you can see those prefixes there. If we're talking just about heat, we'll talk about exothermic, where heat's being given off, and endothermic, where heat's being put in, as different words associated with energy changes. So if we talk about how the world works in a lot of ways, it is through this process. Plants store energy. That energy comes from the sun, and they're able to do something called photosynthesis, where they take carbon dioxide and turn it into carbon dioxide and water, and turn it into the components of the plant, as well as whatever fruit or whatever we might obtain from the plant. And so that's energy going in from the sun, right? And then we can consume that plant matter either by, for example, eating it or digesting it, or just burning it. And if you do that, that might be respiration in an animal or in a plant. or its combustion in this case with a fire, and energy is being released from that. So that's kind of the circle of life there, photosynthesis and respiration. I won't sing the song for you. You'll thank me later. So we talk about substances as being high energy substances, that is, that they have a lot of potential energy stored in them. And then you might also refer to things as stable, that are kind of downhill at the energy sense, that they're not going anywhere. They don't have any potential energy. So they make a little story about the formation there. So here's a picture of high energy and stable. If you have a baited, cocked mouse trap, that's high energy. If the mouse sets off the trap, then the spring is released and the device closes, and that's a more stable thing. And on the right hand side you see the synthesis involving CO2 and H2O to make this compound that is a higher energy or lower energy compound, I guess is what they're suggesting there. From that, actually that is not CO2, that's 2 C's and 1 O, so C2O, and this is H2O, and that's forming C2H2O2, so they're saying that compound is more stable than C2O. We know H2O is pretty stable, right? But so that must tell us that this thing must be unstable. We know H2O is stable because we find it everywhere, right? Water is very common. So anyway, and it's a simplified structure. They're leaving some stuff off to get that, but that's the idea that we have. We can recognize, just like you can recognize in a physical sense, if something is unstable, we can do it chemically once we learn how to recognize those things. So I mentioned exothermic and endothermic before. We've already talked about that. All right, so now we'll say a few words about the scientific method. I think there's a lot of debate about how to frame scientific method discussions. First of all, most people call it the methods of science now, not the scientific methods, because, or we'll even say the nature of science, the nature of science. The suggestion, these scientific methods suggest that there's only one scientific method, and that's certainly not true. Basically, their little diagram there about making an observation, formulating new ideas, and test those ideas, which then lead to more observations. That's not a bad representation of it. That is okay. I'm not gonna argue too much with that. One thing that I do want to emphasize is the issue of hypothesis and theory, and theory and law. So first of all, theories and laws, there is no relationship between theories and laws. Let me back that up. It isn't like a theory becomes a law over time. Okay, they do different things. Scientific law describes observations from circumstances. So, for example, the one I usually use is the force due to gravitation. Isaac Newton came up with essentially this equation that says the force due to gravity is equal to a gravitational constant times the product of the two masses, so the Earth and the Moon, for example, divided by the square of the distance between the two, which is r. So this would allow you to predict how much force due to gravity. And it works really well. Now, but what it doesn't tell you is it doesn't tell you how does gravity happen. How does the Earth know that the moon is there and vice versa, so that they interact and produce this force? Is there something that travels between the Earth and the moon to communicate the information? That theory might be something called gravitons. That there's some kind of particle that we haven't detected yet that carries that force. I think that's probably considered a less supportable theory, but I think some people still formulate work in that matter. Einstein talked about the curvature of space-time, that mass causes a defect in the curvature of space-time. So if you think of a blanket being a representation of space-time, that's a blanket's kind of a three-dimensional thing. You can go one way, you can go, to the left, you can go up and down, left and right, up and down, and then you could go the other direction, 90 degrees angle up and down. So I guess I should say to the top and the bottom of the blanket, to the left and the right of the blanket, and then closer to the bed or higher, further away from the bed. And so if you put a bowling ball on that, you can imagine that the blanket kind of sags down. And if there's a baseball near the bowling ball, that also makes it sag down, and that somehow that sagging in space-time gives rise to the gravity. So in this case, so that's a theory of gravity as opposed to a law of gravity. And again, the law isn't any better than a theory. I mean, you have to have a theory to explain the law. A theory gives you much more predictive insight in terms of how can we affect it. I always talk about the anti-gravitation things you see in science fiction movies, that we'll have those when we really understand the theory of gravity better. The other thing is the idea of hypothesis and theory, that a hypothesis is a baby theory. I don't go with that either. I don't think a hypothesis is a baby theory. A hypothesis is essentially a testable prediction. So if gravitons, for example, is your theory of gravity, then a testable prediction was that if I come up with something that intercepts gravitons, the gravitational force will be reduced. And so if you develop that substance that intercepts the gravitons, and again, that's a whole nother if kind of thing there, that you could then test that prediction of that theory. And again, that gets to a lot of times what scientists are spending their time doing is setting up these tests, which can sometimes be quite elaborate. A lot of times chemists will try to synthesize a molecule, and along the way to try and make this molecule, they have all kinds of theories that they're using, all kinds of hypotheses that they're testing. The whole thing they're doing to produce the molecule is so that some pharmacologist can then test the hypothesis that molecule might cure a certain disease. So I'll post another video of this that goes over this a bit more. But that's my brief version on theories and law. So that's my take on chapter 1, and we'll see you in the next video.